for clay consolidations, I should say primary, the primary consolidation of clay. Because I think this lecture I will touch base on the secondary, but just a little bit of it. I don't expect you to know how to do the analysis. But like we are talking about primary consolidations from clay, and this is the second part. Now we look at the time domain. We look at the time rate of the how this to be happens. So time does matter how fast. It does matter. Depends. It's the salt properties. We learn from the hydraulic conductivities, the K values, the hydraulic conductivities. If you have a different like well, hydraulic conductivities tells you how easy the water is passing through the clay. And consolidations is about the squeezing out the trapped pore water within the clay matrix. So the hydraulic performance of clay matters. It dictates how long does it takes for the trapped water goes out from the clay layers. That contributes to that resulted in the questions of how fast for the consolidations process to be finished, which means how long it takes for the waters to be squeezed out. So some famous case history, if you like, see about all this like engineering wonders, the Leaning Tower at Pisa, the Pisa Towers. So the whole thing there's a huge arguments whether this is a structural or geotech problems. And I think this time the geotech wins. It's the geotech problems. So John Berland from the Imperial College at the British, he come out with a geotechnical approach just to save the Pisa Tower. So he becomes a famous case history, like 10 years ago. So if you read about, if you Google it, you will see about all this. There's even like I feel like classic paper to talk about how to save or how to mitigate the ground problems, the geotech problems, for the foundation problem for the Pisa Towers. So it takes a long time. Partly of it is a consolidation problem for what's going wrong with the Pisa Tower. It's a very like a long time-wise like a consolidation problems. It takes almost 1,000 years. It takes about 1,000 years, and the consolidation is still happening. So that's what happened at Pisa. But for somewhere near Mexico City, it goes down much quicker than the Pisa Towers. So Pisa Towers, if we calculate the rate, it's go down about 0.2 inch per year. But for the Mexico City, it go like go by like 10 times faster, more than 10 times. It go by the ground is sinking by estimates 2.5 inch per year. So like so that's why the settlements problem is much more concerned in Mexico City than like in France, in Paris. So that's why like Mexico City or Mexico actually produce a lot of like a famous or very like well respect geotechnical engineers, because they have this problem, soft ground issue, back home. So Mexico, the soft clay problem in Mexico City is very well known. It's very well known. So it's about the time range of consolidations. Remember, like at the beginning of last lecture, we talked about the spin analogy. So the spin analogy is also captured on what happened here, which is a time domain. Don't forget about this. There's a time domain for this happens. So we have been trying to calculating the deformations. So by how much like the whole systems to settles or to deform, but don't forget about there's a time domain. How much time for the water to squeeze out from the setups. And it also highly depends on the one salt properties. which is the hydrodynamic conductivities, the permeability of the clay. The smaller the holes here means like uh, uh, the less permeable for the soil we are working on. So when we have a clay layers, and when we are compressing on a clay layers, realize that we will have the applied stress. So this is kind of like the loading from the surcharge. So this is the surcharge loading. The surcharge loading. We compress on the ground. But before actually I should put this first. So before we have this like a surcharge, we already have this static pore pressure. So this is the static pore pressure. So U stands for the pore pressure. Remember how you calculate the pore pressure equals to the unit weight of water times the depth. So that is the static pore pressure. Before you loading the applying the surcharge, you have the static pore pressure already. So when you plot the pore pressure versus the depth, so this is the static pore pressure, which is equals to the unit weight of water times the depth. And now we are loading loading with the surcharge here. So you apply kind of like a constant loading at time equals 0. Just like our spring analogy, right? At time equals 0. The water carrying all the loading. We talked about that last time. So once like could be like a structure, could be like a field, you compress on the ground at time equals 0. All the loading carried by the water. Because like water is more incompressible than the soil grain, than the soil. So at time equals 0 is the water fueling all the loading. So that's why the pore pressure will go up at time equals 0. But like so this is the pore pressure at time equals 0. But like if we wait, so if these two add up together, so this is the pore pressure. So here is the change of effective stress. So at time equals 0, we have the static pressure, and also we have the surcharge. So this add up, bringing the static stress to a larger amount by the amount of surcharge loading. But like through times, the water will squeeze out. So at times equal infinity, if we wait long enough, all the water that can squeeze out will be squeezed out. Then we will go back to the static pressure. So that's like time domain over there. And we need to find out by how fast the time rate on how this to be happens. Because like if you have a soil site, or if the structure that you are designing, like a residential building, just you design for the lifespan is just 100 years, and you find out the settlements to be occur to take place to be like 300 years, then like you don't after 100 years you don't concerned about like the settlements from that point. So that's why finding the time for the settlements to be happens is also very important. So one more time, the consolidations is due to the squeezings of the water, which means the technical terms of that is the dissipations of excess pore pressure. So this process over here, so the dissipations of pore pressure is the progress here. So this is that's what does mean by the dissipations of excess pore pressure, because the surcharge will induce a loading at time equals 0, and through times the pressure will be dissipated because the water has been squeezed out. So the water right there will squeeze out to release the pressure. So that is consolidations. And this process takes times. It depends on the hydraulic conductivities of the soil, which means the spring analogy, the piston opening right there. How fast for water to get out of the clay matrix. And also the drinkage path, we talk about this. So the drinkage path is the thickness of the clay. So if you have a very thick layers, then like the water will take a long path to escape your clay. So this is kind of like the clay layer, for examples, versus if you have like a relatively thin clay layers, so water will take a much less distance to travel through your clay to being out of the clay layers or the clay matrix. And now we try to have a better look on this effect in the laboratory, because like if you want to understand this in a better in a more scientific way, we do in the lab, in a sense that we can control the boundary and control other factors. So we can look at the controlling factors or the single issue, or like the dependence of parameters that we want to focus on. So we bring this liquid soil samples back to the lab under the setup of a consolidation test, which is the odometers. So this is exactly the same odometer test you have been working on from the previous lecture. But now we take a closer look on the excess pore pressure. So the same setup again, you have the soil samples. It is sandwiched by two porous stones. Oh, sorry, this is single drinkage. So the drinkage boundaries matters too. And now we just talking about single drinkage. So the drinkage path, you make up with the distance and also make up with the boundary conditions. Now we are at the boundary conditions of single drinkage, and we will talk about double drinkage later too. So in the case for single drinkage, pretty much like we assume the bottom part, either the top or the bottom wall part, is not permeable. So to simulate that in the lab, you can be using a steel block. So water cannot travel through steel. So the water now is only forcing to go to the top where you have a porous stone. So this layers is impermeable. And when we're loading on this setup, we can try to measure the change of the excess pore pressure. So the delta U is the excess pore pressure, which means the pore pressure, the water pressure induced by the loading. U is pore pressure, and delta U is excess pore pressure. That's the terminology in geotech. So just like the same concept as the previous slide. So once we load on the our clay samples here, we have an excess pore pressure that is equals to the induced loading. So the whole slide here is tell about delta U, excess pore pressure. So this should go up. So there's a typo here. So delta U, which means the x-axis, and the y-axis is the depth. So the z should go there. So we kind of like upside down the y-axis. So z is the depth along the soil samples. So this is the depth. And we realize that at time equals 0, across the whole like a soil sample depth, they are filling the same amount of delta U. Just like once you load on it, the water is carrying the loading. So the water pressure is the same across the depth of the whole soil samples. But now what being different now is through times, you will have dissipations of excess pore pressure, but it depends on the depth, which means like if you wait at the boundary right here, for the pore water that was captured near the boundary, you escape much easier than the pore water that needs to be captured at the bottoms, because it will take relatively longer distance to travel. So which means the pressure at this point should be much higher than the point here. The pressure at the bottom is much higher than when you're near the escape boundary. In the return, we can expect a curve like this. So when we are close to the boundary, all the excess pore pressure are gone. So you don't have any excess pore pressure, because once you low on it, all the water here goes out. But at the bottom, it takes a long time. So with time, get a curve like this. And eventually, all the pore pressure, excess pore pressure will be gone. So at time equal infinitive, all excess pore pressure are gone. So we expect a cone shape like this. And if we look at like this picture in maybe like just like talk at any time stock that we have. So we are talking about this curve here. So this curve I try to draw out here is same as this curve. So what does it means on this like a particular like a time slot is on this side of the curve, those are the dissipated excess pore pressure, which means like right here, right here at this level, you know, like at this depth right here, when you're very close to the boundary, the open boundary, all the water pressure is already be dissipated. And at the other side of the curve, right here, what does it mean by that? Is those are the remaining excess pressure, which means like at this part of the curve, those are the pore water or pore water pressure still being get trapped. So at the bottoms, right? At the bottoms, you have a lot of water pressure that still get trapped, because you take a long distance to go out. So with these illustrations, it introduces us another important parameters, what we call the percentage of consolidations. Because as our engineers, if we want to find out the time, which means we need to find out, well, we need to quantify how much water, how much consolidations, which is how much water has already been squeezed out at the given loading. And the definitions of the percentage consolidations is the water that has been dissipated. So in this case, it is the green area that we talked about on the curve before that, divided by the total, right? The total part, which is both the green part and the blue part being make up, and then times 100%. So that's the conceptual definitions of percentage of consolidations, which is the amount of dissipated like a pore pressure divided by the total pore pressure that you have. So you could imagine this delta U is proportional. It's proportional to the amount of water being squeezed out. So the second scenario now we're dealing with is the other boundary conditions where we have a double drain gauge. So when we have double drain gauge, which means like when we simulate this in the lab, we have both porous stones, both top and bottom. So now the water can escape from the soils, from both the top and the bottoms. So you could expect that the shape that you have now, when we look at how the pore pressure change with time, so this delta U should go up here. We're expecting a cone shape, right? So this is T1, this is T2, and this is T3. So for both of them, we are saying like a T infinitive is greater than T3 is greater than T2 is greater than T1 and greater to T0, which is time equals 0. So the longer you wait, the longer it takes for the times to escape the longer you wait, and then the more excess pore pressure being dissipated. And eventually you go back to T equal infinitive, which means all of them are gone. But you also couple with the depth, and now you can visualize that it is the middle part for double drain gauge, right? It's the middle part. At the midpoint is the one that have the longest drain gauge path, because both the top and the bottoms, the water pressure can be dissipated like immediately, almost. But the middle is the one that like take the longest way to get out from the clay samples. So if you try to draw this out, right, the percentage of consolidations, this will be look like this over the total one. Now you have a cone shape. So those are all those observations from the lab, and like Tosagi, which is the father of geotechnical engineering, more than 100 years ago, he started to look at all those issues in the lab. So he has the observations for him to calibrate his mathematical model. So when we talk about mathematical model, will be this one. This will be the famous Tosaki theory in 1925 that he tried to find out the time rate of consolidations. So he based on a setup. He based on like fundamental like equilibrium equations with like thinking about salt elements. So this is a salt elements. When water trying to flow through a salt elements, which is the inflow and the outflow. So the inflow is VZ right there, and in one directions, and the outflow will be the inflow plus the change of the flow in the Z directions. So I think on Canvas I should have already uploaded like another documents. I try to walk you through like the whole progress, how it works. So if you go to like Canvax, I believe like the tab under Lecture 9, and that's a file called Tosaki 1D consolidations. Then like I try to walk you through the whole progress. So when I was undergrad, I remember when I was taking this class when I was undergrad, I spent a whole weekend. I tried this. That's why I paused you. I spent a whole weekend trying to understand the Tosaki theory, and also I try to code it with MATLAB on generating this cone-shaped curve. So at the end of the day, what Tosaki has done is he set up the kind of like a mass balance equations from static equilibriums on looking at how the water goes in and go out of salt elements. So that's what exactly what consolidations is doing, right? It's about the poor water escaping the clay. So which means the clay water trying to go through our salt elements, going in and going out. So the squeezing of the water is the process of consolidation. So that's why what he started. So from some basic equations on the flow of the water, and then also make use of Darcy law, and then make use of the phase relationship that we learned at the beginning of the semester. Talk about the rate of the change of the volumes, and take out some like relationship from the phase like relationships. He set up the equations, and then he equates the rate of volume change equals the time rate of the volume change in terms of the water ratios. So he has done all this. At the end of the day, this is the famous Tosaki equations. I highly encourage you to try to understand what's going on this PDF. I don't have time to go through all this. If I go through all this, I think it would take like 2 lectures to do that. So I assigned this as a kind of like advanced reading for you guys. If you want to understand the math behind, try to read this like this documents. And at the end of the day, this Tosaki equation is telling us the change of the pore pressure, the BUDT. So the change of the pore pressure with respect to time is related to the depth. Remember like the lab experience, we talk about like the previous 2 slides, we come up with the cone-shaped curve. So this equations reflect the relationship between the change of the pore pressure with respect to both the depth and the time. And the beauty of this, he only used one single parameters to relate that. So this was a huge findings back to 1925, is about 100 years ago. So this is great because like before this, like try to simulating or try to find out the time rate of settlements is almost impossible. But this Tosaki, he come up with a simple yet elegant formula to represent the whole concept. I mean the whole phenomena of consolidations. And down to the point that if you can measure this parameter C sub V, so C sub V is the the coefficients of consolidations. So we spend time, actually when you take the 360 laboratory class, you will spend time to learn how to measure these parameters. So this is the coefficients of consolidations. So this is the famous like Tosaki equations. And if you guys want to understand how to get to this point, then go ahead read the PDF files. And in practice, well, at the end of the day, if you want to solve for everything, we need to solve for this differential equations. We need to solve for this differential equations. And this come from 1925, and back to old times, before the computations being popular or being accessible for daily use. To solve for the differential equations could be very time consuming. So Tosaki, he further developed the solutions, the graphical solutions of the of this differential equations right there. So this is what we use. You can use for design. So percentage of consolidations right there, which is the x-axis, is equals to the depends on the depth. So this is the depth. The y-axis is the depth, and the this cone-shaped curve over here, which is the solutions for the differential equations. Those are the time factors, and the time factors is here. So this t sub v right there is the t right there. So this is the time factors. And this is the time factors in the vertical directions. Is equals the time that you're looking at, and also this is the drinkage path that we also talk about. The drinkage distance or drinkage path, and it related to the coefficients of consolidations. So which means if you can measure this, the coefficients of consolidations in the laboratory, the consolidation test allows you to do that. So in the 368 lab, again, we spend time together to learn how to measure these parameters. So once you get this from the lab, and for the geology, you know about the drinkage path, which means the thickness of the clay layers, and also the time that you're looking at, then you can calculate the T sub V, the time factors. And if you know the time factors, and if you know the depth that you're talking about, so this Z here is the small z, here is the depth of interest. And the H here is the thickness of the clay layer. So if you know all this, and then you can, if you know the time factor, and then which means the cone shape, which contour line you're talking about, and also if you know a particular depth you're working on, then you can find out the percentage of consolidations, which relate to the time rate. So any questions from there? I guess maybe trying some examples will help you. And your next homework, which is homework 8, I would say the next homework can be the most challenging one throughout the semester. I will make sure to find out the pore pressure distributions throughout the depth and throughout the time. So there's 2 dimensions right there. So to me, design work, this is enough, knowing how to use this graph. But I highly encourage you to know about the meaning behind this design chart. So this is what we call the design chart. Just like when you do the stress distributions, remember back to a couple lectures ago when we talk about stress distributions. we talk about all this contour line, right? This is the design chart, all this curve. If you wonder where this curve come from, they are very likely from closed form equations. Very likely could be a differential equations. So if you want to be the real engineers to able to to make a difference in your career, I'll put it this way, you better know what behind this design chart. Which back to our consolidation topics. Whoops, which is right here. The better engineers knows like how to come up with this contour line, not just using them. So so I borrow Captain's Morpheus here. So if you want to, I forget which pills. Remember like the red pill and blue pill, or maybe you guys are too young for this movie. So like when I was taking this class, like my age, is this Matrix is my college time. So red is the reality, right? And blue is you still stay in the matrix. So if you want to go beyond the matrix world, which is like you want to see all the coding behind, you better like read this. I highly recommend encourage all of you. Try to like do the math derivations yourself. Form a piece of soil elements. Water squeezing out from or water migrate through the soil elements from the mass balance equations, and then come up with the differential equations, and then solving for differential equations. At the end of the day, you should get the solutions. So this is the solutions of the differential equations we talk about. And when I was undergrad, I spent time on trying to coding this, and I think at the end of the day, I understand what's going on. So I highly recommend you guys, when you get the time, try to do it. It's not required that I won't ask you, or if you want again, but like in the final exams, I won't ask you to divide the formulas, but just ask you how to use this design chart. But I highly encourage you guys try to truly understand what's going on. So this is another one to give you the relationship, just the time factors and the percentage of consolidation. So this try to take out the effect of the depth. So should the relationship between the time factors and the percentage of consolidation. And this is the equations for the time factors one more times. So at different like a percentage of consolidations, you have different time factors. The time factors is dimensionless parameters. So for example, at 10% of consolidations, you have a time factors of 0.08. And the theory of Terzaghi, it only works for primary consolidations. So this design chart over here, or this model here, or all his like a mathematical work he has done, it only works for primary consolidations. So which means when you get close to the end of the primary consolidations, this model doesn't work. So this model, or this like all this design chart we're talking about here, cannot work for secondary consolidations. So that's why when you get close to 100% consolidations, the time factor is infinitive. And it is part of the assumptions that they're working over here. So he has a bunch of assumptions when he start on this. So that's one of them is there's a unique relationship is independent of time between void and effective stress, which means does not consider secondary consolidations. Because like we assume under primary consolidations is only about squeezing out the water. You are not changing the void. But when you get too close to the secondary consolidations, you have already squeezed out the water that he can squeeze out. To that point, you start to be distort the soil particles. So which means you're changing the phase like relationship, which means the void ratio. So that's why like this method doesn't work when your percentage of primary consolidations get close to 100%. Okay, this slide gives you some typical number for C sub V. So which means like again like this whole model depends on one parameter, which is the coefficients of consolidations. And this number is the one that you mean to like you need to find out. So if you have the money, if the budget as a geotech consulting project engineers, you need to represent your clients to find someone to go to the site and then get your soil samples and do a consolidation test, and then you can quantify the C sub V used for design. And the design part we're talking about is the time rate. We try to find out how much times for the consolidations to get done, or to the percentage that we want to find out. So this is some typical C sub V values for different type of soil. So we have the Boston Blue clay, and also we have the San Francisco Bay mud. Those are very soft material. So we got a C sub V values, about like maybe like a 1 to 2 or maybe up to 10 meters square per year. And if we have some like a very kind of like a stiff material, like we're getting like maybe the silt. So silt is almost get to sand, because we know sand is very stiff, and clay is relatively soft, and silt is between the two. And we got a C sub V values of much higher, which means the conductivities of the soil is much higher. In that sense, like we got, you can have a picture that for less permeable material like clay, you will have a smaller number. But if you have a much permeable material like sand or gravel, you will have a much higher number. For example, I think silt, you can have a very high number. So that's an overall silt material right there. Okay, any questions up to this point? So before we do an examples, we also need to, so before we actually doing examples, we also need to talk about the drinkage path with different like drinkage conditions. So we have two different kind of drinkage conditions, both the single drinkage and the double drinkage. So for single drinkage, we're likely, we have one layer that is impervious. It could be a backwalk, which is intact backwalk, or other clay layers. So we know that the water cannot like travel through, or like at least the drinkage will be much slower than the clay layer that you're working on. And the other drinkage layers could be permeable. So it could be something like sand or gravel right there. So for the drinkage path, for scenario like that, we assume the drinkage path will be equals to the thickness of the whole layer. So H0 is the thickness of the clay layer. So this is the clay layer we talk about. And for the case that you have a double drinkage, which means the clay layer that you're working on now is sandwiched by two permeable layers. Could be sand, could be gravel. Then in that case, your drinkage path will be half of it. Any questions here? Okay, so let's try examples like quickly together. So now we are we have we consider the following following like a soil profile. So you have a clay layer that being sandwiched by the two sand layers. So what kind of drinkage is this? Is that single drinkage or double drinkage? Double, right? Very good. And given the thickness of this layer is 100 feet, so what is the drinkage path? So the drinkage path is 50 feet. So this is a double drinkage. And now it asks you how long it takes for 80% consolidations to the clay layers. So remember the Tersagi theory that we talk about, and this is the formula that comes from the Tersagi theory. So which tell us the time is equals to the time factors times the drinkage path square divided by the C sub V. And we are looking at 80% consolidations. And remember this time factors is related to the percentage of consolidations. So if we go back here, so for 80% consolidations, which is this number there, so the time factors for that is 0.567. So the time will be equals to 0.567. And I hope you have understand this, like, where this come from. This number is come from the solutions of a differential equations. If you solve for the differential equations, you got a curve and a particular like a percentage of consolidations, you will get this time factors. And then times the drinkage path, which is 50 feet square. So always solve the units. And the C sub V, which tells you the how fast the consolidations to be happens, which is the coefficients of consolidations. And this number is 0.356 feet square per day. And if we solve for this, we will get 3,982 days, which is almost 11 years. So everything takes times. Okay, next questions. It asks you how to estimate how long does it take for the consolidations to be happens. So how long it takes for the 2-inch settlements to complete for the soil site that we are working on below. And we assume the ultimate settlements is 5-inch. And I also asked you assume the maximum pass pressure is 8,000. Ask you to find the OCL. So don't worry about this part. This is not related to this topic. So don't worry about this. Just ask you about to find the overly consolidated ratios. I know I think at this point like you should be very comfortable for that. 2/5, right? Give you like a 0.4.
Yes.
Which means this is the percentage of consolidations. So if you know the percentage of consolidations, then you can find out the time factors at 40%. So at 40% of consolidations, we got a time factors of 0.126. So with that, For this site, is that a single or double drinkage? It's double, right? Actually, it's the same site. So it is a double drinkage. It's the double drinkage. But maybe let me try something special here. So if this is another like a clay layer, so if think this is a clay layer, then would that be a single or double drinkage? Single drinkage, right? Let's try to solve for this questions for both single and double drinkage. So for single drinkage, and you will find out the time that you need equals to the time factors times the drinkage path squared divided by c sub v. Then that will be equals to 0.126 times, so now for a single drinkage, what is your drinkage path? 100 feet square, right? We got this case 0.29 feet square per day. So, and also we try to work on the case that this is a double drinkage. The time will be equals to 0.126 times, now this is 50 feet square divided by 0.29 feet square per day. And how much we got for years? Discuss this is about 12 years. And how about the other one? How about for the double drinkage? So through this like a two scenario, I want you to see the effect of the drinkage conditions or the drinking boundary. If you have a single drinkage versus a double drinkage, since this is a square right there, so you will take much less time when you have a double drinkage than like a single drinkage. So these two examples give you a very brief idea on the time range of consolidations. And in fact, here, what we're doing, we only talk about the time, the pore pressure or the percentage of consolidations with respect to the time only. We haven't talked about the depth. We haven't talked about the depth. And the next examples, we try to demonstrate you like, to talk about the effect of the depth. So for examples here, the effect of both the time and the depth, and how would the pore pressure look like? And this is not a linear equations, so it got to be a little bit more complicated. Like you will have to have paper calculations may not be enough. Then you need just the point that you need Excel. So for example, this the sites here, you have a compressible clay layer here that you were about the consolidations. Oops. So this is the compressible clay layer, and you are loading on it with the extra fill right there. So this is the fill that you place on the clay layer. So that's why after you're placing the 7 meters of sandy material right there, you want to find out the settlements in the clay. But before that, you want to find how would the deformations look like in terms of both the time and the depth. Because at different time, you have different amount of settlements. And at different depth, you have different amount of deformations too. And then you want to find it out. So to do that, so you will have you will have a very similar homework problem like this one. So homework 8, you will be all about like solving a problem like this, but this time like the homework you have a double drinkage, and for this one, the clay is now sandwiched by like a sand materials and imperious rock material. Then what kind of drinkages are we talking about? Single, right? Single drinkage. So we are solving the whole thing with single drinkage, and we need set up an Excel spreadsheet on this. So this will be my expectation for you, at least like for this cost, like you're able to handle this. And if when you move on, this is 3,000 level. When you move on to 4,000 level, when you talk about all those design costs that you will take, and also for a senior design that you will have, very likely when you got a real world problem, you need to do something beyond the paper. So when you like try to find out all the stresses with the difference of time and depth. This special calculations over there will do that for you. So I believe I have uploaded this on Canvax too. This spreadsheet should be available on Canvax. If not the case, let me know. So I hope like this spreadsheet, you can take a look on it. And when you do your homework, if you get stuck, you can look at my spreadsheet. But the whole idea is for you is you're able to do all this by yourself. Is your educations or you taking the course is not about for you to getting by just one homework or getting by one course or just getting by for the 4 years. You get a degree. It's not just getting a piece of like a certificate, a piece of like a paper. At the end of the day, is about whether you can solve the problems. When you go to work, when you go to practice, no one care about like what kind of fancy school you come from. But anyways, the whole picture here now is we have this site. We want to find out the settlements of this clay layers at different time and different depth. So this is the solutions. So at different depth, so pretty much like this two can can overlap with each other. So at different depth, so from 7 meters to 21 meters, at different depth, we can like find out the different like vertical effective stress, because the vertical effective stress is equals to. So let me try to draw this. Because the vertical effective stress is equals to the total stress minus the pore pressure, and this pore pressure is related to your excess pore pressure that you generate from the field that you place on. So if you can find out the initial this terms, which is a functions of time and depth, then you can find out the effective stress profile. So that's what I'm trying to draw it there. So if you look at like all this graph here. Oops. So the blue line here, we can see legends here. So the blue line right there is representing the vertical effective stress at infinite time, which means this is the static pressure. Because remember we talked about this at the very beginning. Through times, all our like a pore pressure will go back to the original static pressure, or like through times, our excess pore pressure will be all gone, because all of them are dissipated at time equal infinitive. So here, the blue line here pretty much is your infinite stress. So I hope like you're not only able to calculate this on a paper, you also can code it in Excel. If you want to do MATLAB, do it on MATLAB. So to calculate that, at different depth. So at different depth from like a 0 to 21 meter right here. So I have a depth from 0 to 21, and from 7 to 21 is my depth of the clay. So so at different depth, I can calculate the vertical stress. just like how would you do it like on a piece of paper, but now I do it at an integral of like every 1 meters, including like try to capture the interface. So at 3.5 meters is the interface of the water table. So so through different like depth, it's just I let you to look at my spreadsheet, or you guys need to do it for homework too. You know how to like to code it in Excel in a way that you try to find the total stress throughout the all the profiles, and then like you're also able to find out the pore pressure, right? The pore pressure above the groundwater tables, which happen at 3.5 meters. You don't have any pore water pressure, so that's why 0.0000 there. But after like a 3.5 meters, this is your pore water pressure, right? The unit weight of water times the thickness that you talk about when you have discrete elements in Excel. And then you add back the previous terms. So the coding of this allows you to figure out yourself. And at the end of the day, the effective stress will be total stress minus the pore pressure. So with this, you can draw this line, at least the blue line right here, this the static water pressure, which means also the initial pressure, effective stress. And then the next curve that you need to construct to look at is the vertical stress right after you're pacing the field, right? You bring your vertical effective stress from this one to here, just like we talked about at the beginning of the class, at the beginning of this lecture. Once you pace the amount of surcharge, is water carrying all the loading, because like water is relatively more incompressible than soil. So the loading won't pass on to the soil grain. The clay is not feeling it, but just the water. So that's why your water pressure will shoot up. And we can calculate this too. So the surcharge loading is right there, which is equals to the unit weight of the soil, which is the sand, times the thickness of the sand. So this is the unit weight, and then times the thickness of the sand. That gives you the total loading, the surcharge of the field. So that's why at time equals 0, then we can calculate the stress, which is exactly equals to the vertical effective stress times the total plus the total loading. Then you will get this like a strict line right there. And then after that, we can also calculate the other important terms. So get up to this point. I hope like at least you feel comfortable on this, on getting the blue and the orange line. So before and remember this is the famous Tosaki equations that giving us the solutions of this problem, the time range of consolidations. And if you truly understand, or if you like work through the deviations, which I highly encourage you guys to try that, you will realize the change of pore pressure. So the time range of consolidations is all about the excess pore pressure dissipations. So because you're loading on the ground, and like you induce the pore pressure, and now through times, how long it takes for the pore pressure to escape your clay matrix. So that's the idea of the time range of consolidations, and the dissipations of the pore pressure depends on two factors. Depends on the time, and which is the dt right here. Also depends on the depth. So it's depth and also the time related. and like you proportional to a constant, which is C sub V over here, to coefficients of consolidations, which is the soil properties, which means like, sand versus clay, the different type of soil give it different properties, and end up you have very different responses in terms of the time rate of consolidations. So we talk about all this, and then we have done like two quick and easy examples. Examples 1, example 2, we just look at the time, but we didn't look at the depth. But example 3, and we try to we finish this quickly today. Question 3 got a bit more complicated now. Is we work on the scenario that not just about the depth, it's also about the not just about the time, but also the depth. Which leads us to the spare sheet that we look at. Remember, like the questions, what is talk about is you have this clay layer here. And then we are loading the clay layers with an additional like layers of fill materials right there. And we want to know how the effective stress change when this clay layer is loaded. Because when we're adding an additional fill, which means we surcharge or loading on the clay layer, what you change or what happens within the clay is there's consolidations happens, which means so consolidation happens, which means like the excess pore pressure or the pore water being dissipated, excess pore water being dissipated, which will result in the change of the pore pressure. And the change of pore pressure, we change the vertical effective stress, and which is the design interest, the vertical effective stress. Because later on, like when we go to the last topic of this class, when we talk about the shear strength, the strength of the soil, it highly depends on the vertical effective stress. So here, pretty much like at this graph, I give you the solutions already. So it shows you like along the depth, how the vertical effective stress look like. The orange line to start from this like a light blue line, which is the static vertical effective stress. And we can do all the calculations right here throughout different depth. So from 0 to 21 meter, which is the clay layer is starting from 7 meters to 21 meters. So this is the clay layers we are looking at. But throughout the whole soil profiles, we can calculate the total stress. So this pretty much is your homework, your lecture number 3. You went through this with homework number 3 and also your exam number 1, how to calculate the total stress. But now you need to code it in Excel. So you guys will have a chance to work on your homework. On paper, I highly recommend you like try to see whether you can solve it with Excel, and then like get a piece of paper and a pen, see whether you can also solve it on a paper, and to double check your Excel like coding are correct. So you calculate total stress, and also based on the locations of the water table, you can calculate the pore pressure. So the water table happen located at a depth of like 3.5 meters. Then that's where the pore water pressure gets started. So again, like coding how to calculate the pore pressure, and at the depth of 21 meters, you got like a pore pressure of that much. Then the effective stress that you calculate pretty much is the difference between the total stress and the pore water pressure. So this point, like we should be feel very comfortable on that. And this pressure right here pretty much is the light blue line, the static vertical effective stress. So after infinite time, all the excess pore pressure has already like dissipate out. So you go back to the static pore pressure. So this is pretty much like a time equals like a infinitive. So you look at this plot again. So this is the time equal infinitive. And
at time equals 0. So right after you put on the fill layers, this orange line here represent the excess pore pressure at that time, and the difference between the orange line and the light blue line right there is a constant, and the constant is the loading, the surcharge, because at time equals 0, all the loading goes to the water pressure, because like a water is relatively more incompressible than the soil. So that's why at time equals 0, the water is carrying all the loading. So this is the water pressure. Sorry, this is the stress at time equals 0. So to calculate this terms in the clay layer, pretty much is your vertical effective stress that you have calculated times the surcharge loading. So this is the surcharge loading. And the surcharge loading is equals to the unit weight of the fill. So this is the fill layers, the unit weight of the fill. And this is the clay layer, the unit weight of the clay. So the verticals, the surcharge loading will be equals to the unit weight of the fill layers times the thickness of the fill layers, which is 7 meters. So 7 meters is the thickness of the fill material times the unit weight. So the unit weight times the 7 meters give you the pressure, which is the surcharge. So at the end of the day, this loading will be the vertical stress plus the total loading at time equals 0. So this is the time equals 0. The next step is to find out the pore pressure dissipations, and we know that the pore pressure dissipations, if we understand like Terzaghi, it's just solving this differential equations. But back in the Terzaghi time, they provide a very nice graphical solutions, which is this one. This is the solutions for this differential equations right there, which is the functions of the depth. So this axis is the depth, and the percentage, and the x-axis is the percentage of consolidations. So now we need to take care of the depth factors, and this ratio here is the depth of interest. So this small z over there is the depth of interest, and this depth, very important. You need to realize this point, and this depth here, C is start from the top, from the depth of the clay layer. It's not to count the z. This z term here is not all the way from the ground. It's from the clay layer that you're looking at. So that's why here, depth of 7 meters, you have 0, because this is where your small z start from. And it normalized by the h. H is the thickness, of the clay layers. So in this case, it's 14. It's 14. Actually, it's a drain gauge. It's a drain gauge layers. So here is the thickness of the clay. Is the drain gauge thickness. Actually, the better way to say it is the drain gauge thickness. And our case here, so this H is the drain gauge thickness. And in our case here, we have the clay below the sandy material, and on top of like the intact rock. So if this is a single drain gauge, then what is the thickness of the drain gauge? What is the drain gauge path for this case? That would be 14 meters, right? Because like if it's a single drain gauge, so we talked about this like last time. So the drain gauge path, right? So if it is like a single drain gauge, so pretty much the whole thickness is your drain gauge path. But if you have it happens as a double drain gauge, the drain gauge path will be half of the thickness of the layers. So these examples, we work on single drain gauge. Pretty much I showed you a single drain gauge. And like in your homework assignment number 8, you will do it for a double drain gauge. So back to this graph. So the capital Z right there will be like the depth starting from the top of the clay, normalized by the drain gauge thickness. So back to our spreadsheet. To calculate this like a Z over H, yes, pretty much we count from the top of the clay layers. So pretty much like all the depth minus 7 divided by the drain gauge path. So now with this like a depth terms right there, we can find out at different like times. So the questions ask you. Let me go back to questions. This is so the questions didn't ask you the specific time, but like we want to demonstrate. We want to demonstrate at different period of time how would the vertical effective stress change. So I pick 1 year, 5 years, 10 years, and 15 years. It can be any times. It can be any times. So at like a 1 year, 5 year, 10 years, and 15 years, we can calculate the corresponding time factors. So the corresponding time factors. You go back to the Tosagi theory. Remember the Tosagi theory? It has this time factor right here. So the time factors is equals to the coefficients of consolidations, which is given in this case. So the coefficients of consolidations is right there. It's a soil properties. If you get a soil sample, you conduct a consolidation test or odometer test, you can get this number, which is 9.3 meters per minute in this case. So these are soil properties. We have it. And then times the time. So the time is the particular time spot you're looking at can be any time. So our case is 1 year, 5 years, 10 years, and 15 years. And then divided by the square of the drain gauge path. That gives you the time factors. And where this come from is part of his like a solutions of the Tosagi equations. So at the specific time slot you're looking at 1, 5, 10, and 15. So this question didn't specify it, but I think in your homework, next homework, you will do a very similar exercise. And I think I asked you like look at 10 years and 40 years. Time equals 0. So time equals 0, 10 years and 40 years. This will be your homework assignment number 8. So you work on a very similar problems on homework number 8. So you have like a different time, and then like you can calculate the corresponding time factors. Because you know the C of V, you know the drain gauge path. You also looking at the time that you're looking at. So with that, you can find out the percentage of consolidations through this graph, right? Which is the solutions. The solutions of the solutions of the Tosagi equations. For examples, on let's pick this one. Let's pick this one. So at the depth of 9 meters, so it's like a 2 meters into the clay layers. So the Z over H is like 2 meters. So 9 minus 7 is given 2 meters. Normalized by the drinkage path, you got like a 0.14. So the Z over H is 0.14. And we look at the time span of 1 year. And at 1 year, we got a time factor of 0.047. So with that, the Z over H is 0.1, right? Did I say 0.1? So the Z over H is 0.14. So this is half. So this is 1.5. So 0.14. So this is 0.25. This is 0.5 right here, and this is 0.25. So 0.14 somewhere around there. So I just eyeball it really quick. I may be wrong. So, but you get a point. You try to find 0.14 on the y-axis, and then now you look at the contour line. You look at the contour line that like equals to 0.147, 0.05, right? So now we look at the contour line equals to 0.047 because we are looking at this depth and this time. Again, the whole thing, the solution of the Sagi is about the depth and the time. So we know this depth, which is corresponding. We know this depth. We're looking for this depth, which corresponding to this like a ratio, and this time corresponding to this time vectors, which is 0.05. So this is the 0.05 curve at about like a 0.15, 0.15, right? Sorry, I keep forgetting numbers. It's about like a 0.14 on the y-axis. So, which is this point right here, which is this point right there. So I know I'm looking for this curve, this contour line, and particular this is like a 0.14. So about this point, and this go back to my x-axis is about right here. It's about I think it's about 0.6. I didn't pick this point like our accurate, but like but you get how to do it. So you know the y-axis and you know which contour line you're looking at, and go back to x-axis. Then that would be your consolidation ratios, U sub z. So you know this how you get this like a consolidation ratio. So any questions from there? So you need to know how to do this for the next homework, and very likely you'll be come up in your final exams again. Mm-hmm. So this is the C sub v. So this is the C sub v, and this is the 1 year, and this is the drinkage path. So the next items after we calculate the time factor. So make sure you know how to get these time factors. I would think like for some of you this is the most challenging part. But if you like really study my spreadsheet and then try out the homework, then you should get there. And I got the next thing will be calculating the dissipated pore pressure or the like a remaining pore pressure. This should be the remaining pore pressure. So the remaining pore pressure will be 1 minus the consolidation factors times the total pressure. So this part is the here. This part here is the remainder. Whoops. Excess pore pressure. Which is equals to 1 minus the percentage of consolidations times your total pressure. Just remember this. This is the we mean the excess pore pressure. The dissipated excess pore pressure will be equals to the percentage of consolidations times the total pressure. Remember, we talked about all this concept last week. Right there. We talk about all these concepts right here. What being remained and what being like dissipated. Now we are talking about the remainder pore pressure. So after we know like the remainder pore pressure, the final stresses will be the static pressure plus the remainder pore pressure. So that's why each of those like are contour lined. So that's why at the end of the day, each of those contour lines, for examples, so the great one is after 1 year, will be like the pressure right there. The static pore pressure plus the remaining excess pore pressure. So this is the static pressure. So this component here, which is the static pore pressure, sorry, the static stress, the static vertical stress, plus the remainder excess pore pressure. And the remainder pore pressure is highly related to the percentage of consolidations. So that's pretty much I give you the whole solutions already for this example problems, and it is very similar to your next homework number 8. So I would say the homework number 8 is the most challenging one, and like if you want to get a sense on what engineers do at work, it's not like homework 1 to homework 7. You have a textbook problems just to do one part of it on the paper, but you will be like this homework problems. This homework I mean to challenge you a little bit, because at the end of the day, engineers, what they come up with is a graph like this to present the overall picture or the results on the whole site look like. So I highly recommend you, if you are like if you want to challenge yourself, don't look at my example spreadsheet when you try to solve the whole thing. See Pro Excel, use Excel. I think Excel is the best way. You can use MATLAB, but like if you want to code everything at the beginning for being correct is hard. But Excel is kind of like open box. You can do it like you can like have the visualizations cell by cells what you're doing. So try to set up Excel spreadsheet to solve for homework 8. And if you truly understand what's going on, at the end of the day, you should get those like a cone-shaped curve. Be very careful. Your homework 8 is double drain gauge. It's not single drain gauge. So you'll be expecting like a cone shape rather than this like a semi-cone shape. So the next slide after examples number 3 is talk a little bit about the secondary consolidations, which is a topic that we will talk in CE 4670. Right? Is it 4770? Yeah, I think the foundation class is 467. We talk more about that. Like the key but I like this graph here give you a sense on what's going on. So when you're loading on clay samples or clay layers, so you will expect you have immediate settlements. Then this is for clay. Sand will be a different story. And then like you expect most of the deformations is from the primary consolidations. So that's why we spend so much effort, because there's a significance, particularly for clay. But after which upon that all the water that can squeeze out from the loading has already been squeezed out, the deformations continues. And that is the secondary consolidations. But that times it's not by squeezing our water, it's by the deformations of the soil particles at the constant stress. So pretty much like you keep deforming and like no water comes out, but it's still like are going down in the secondary consolidations. Is because now it's not the water coming out, it is from the deformations of the soil particles. So this topic you can go on for a week, but like I just want to give you an overview. So that's the secondary consolidations, and there's some like typical parameters right there. We talk about it in 467, and last but not least, remember what is soil consolidations. So we talk about this like at the beginning of like the previous lecture already. So what is soil consolidations is pretty much is about squeezing out the water from the clay, and the important factors. Remember, like this is like time, the formations, and loading phenomenon. So that's always 3 dimensions: time, the formations, and loading. And it is that's an important fact is it remember the stress history, which represented by the maximum past pressure. So soil remembers, the clay remember the maximum loading that you have ever been experienced, and we can recover that. That is the maximum past pressure. So we talk about that too. And there's 2 more interests, right? Which is the compressibility, the matter of how much, and also the time rate, the matter of how fast. All right, with that, like we finished the topic of consolidations, and according to our